So here's our definitions of a secant line. It's just a line that connects two distinct points of a function. The slope of the secant line, stuff that you had on your quiz today, the average rate of change of the function over the interval. Okay? How much the function is increasing or decreasing per unit over the interval. So if I look at this secant line from this point to this point, we see that the slope is negative, so the average rate of change between A and B is some negative value per unit. Well, a tangent line is a function, is a line that just touches my function at one point, and the slope of the tangent line turns out to be just the instantaneous rate of change of the function at the point. So here we would say, since the slope is positive, my function is increasing by a certain amount per unit, right at that location, right there. Okay. There's a question on your homework about this guy who traveled 31 miles in 30 minutes. And, is it right for us to give him a ticket for speeding, for going over the speed limit? Well, if we found the average rate of change, we would have found that he averaged 62 miles per hour. Okay? That does not mean, and I saw some people answering, no, we're not sure how he was traveling in that time period. However, we do know that on average, he traveled 62 miles per hour, which means at some point, he must have been going faster than 62 miles per hour. So he obviously had been speeding at some point. Question. What if he took a shortcut? Well, it was 31 miles from one toll booth to one other toll booth on a highway. I'm going to say there's no shortcut. But good answer. What if he took a shortcut? Good point. Yes, you can say that. No shortcuts here in calculus, though. Just tangent lines and instantaneous rate of change. That brings us to, this is really the beginning of the rest of this semester, this lesson, okay? Everything led up to this lesson, and everything after this will be all about this lesson, really, and just applications of it. We are going to define what a derivative is. A derivative is just a fancy math word for instantaneous rate of change. That's it. And I'm going to write it down like that. Fancy math word. Instantaneous rate of change. Well, we know instantaneous rate of change is also meaning the slope of a tangent line. So actually we have three words that all really mean the same thing. They're all interchangeable. It's very important to write this down, that a derivative is the same as the instantaneous rate of change, which is the same as the slope of a tangent line. I'll use three lines for equivalency. Super important. And we'll forget about it, but I'll remind you frequently. Okay, so that's what a derivative is. We're going to be taking a lot of derivatives in this class, which means we'll be finding a lot of instantaneous rate of changes, which means we will be finding the slope of a tangent line. And before we answer our first question, we are going to write down some notation for derivatives. Okay? Typically we say if f is a function, we say that f prime, this is f with a little tick mark. This tick mark we say is prime. It's not like a 1, it's just a little tick mark. We say that's f prime of x. and we say this would be the derivative of f, or the slope of the tangent of f, instantaneous rate of change of f. Okay, good. So we know that. That's going to help me with this next question. Our first question involving derivatives. Well, you've already had a problem with derivatives. We've had the dude and his exact velocity. Well, now I'm going to take a function. So I'm not going to talk about positions. I'm going to take function, the function 3x squared. Here's the function 3x squared. And when x is 1, we should have the coordinate 3. So let's just say that this is 1. And we'll say this is the y coordinate 3. Okay? And the question is, what is the instantaneous rate of change of the function when x is 1? So how's my function, what is my function doing right at x equals 1? Is it going to be increasing? Is it decreasing? By how much? That's the question. Okay? Well, first thing you should write down besides this question are the words that you can replace instantaneous rate of change with. You can place instantaneous rate of change with slope of the tangent. You can replace slope of the tangent or instantaneous rate of change with derivative. And now that we actually have notation, I can write that entire statement with just function notation and derivative notation. This entire thing can be asked of this. F prime of 1 equals what? Okay, so what is this? This is what is the derivative of f, or what is the slope of the tangent of f when x equals 1? Just right here, this means all of that. Now, if you've taken physics C, or if you're taking physics C right now, just pretend like you're not in that class. And we're starting over from scratch, okay? So if you have any rules that you know, there are no rules, okay? We're just treating this as a new situation, okay? Well, what could I do to find this? Can I use my calculator, say, to find this? And that's how we're going to start. And we did it kind of last time with the idea of using our calculator, but we didn't actually use our calculator. But how could I actually do it this time? Any ideas from the gallery? What do you think, Ms. Kruthi? Perfect. We're talking about slopes, right? And slopes at points. Well, we know the slope is just this equation, right? Simple stuff. Well, that means I just need 2 points, right, to find the slope. Well, Ms. Kruthi picked 2 great points to use. She said, why don't we use 0.9999999, and why don't we use 1.00001, and why don't we find the slope between those 2 points? Because we can't take the point in itself, right? If I just use the function value 1, which gives me the y value of 3, I can't just say, okay, the slope at 3 is going to be 3 minus 3 over 1 minus 1. That doesn't work, right? That gives me an undefined value, 0 over 0. So I need 2 different points, right? But that's not saying the points have to be 1 or 0 and 2. We can pick any 2 points as long as they're not on top of each other. We could take any 2 points and find the slope. Well, let's take the point f of 1 minus, so let's go f of 1 plus and subtract f of 1 minus, and then divide that by 1 plus minus 1 minus. And what do we use for that? Well, we used 1.00001, say like that. Now we could go closer, right? I could put more zeros. And I could plug that into my calculator and figure out what the function value is. So I have 4 zeros here. And I also can take 0.99999. So let's do 4 nines. And I can find out what that's equal to. Well, why don't you guys do that? Why don't you guys use your calculator? Why don't you figure out what these y coordinates are, and let's take these 2 points that are really, really close together, find the slope between those 2 points, and you know what? We could probably take a guess as to what the exact value would be if these 2 points got even closer together. Go. Use your calculator. Do it. I'm going to do it on Wolfram because they do not round. And they like big numbers. Nope, don't like that. What do we get for our function value at 1.12341? What is this function value? 3.123406, right? And you know what? It might be even different than that because our calculator might just stop. What about 49 squared times 3? 2.99940003. Well, when you plug that y-coordinate and the other y-coordinate up here, and then we plug in these x-coordinates up here, what do we get for our slope? We got 6. Our calculator told us 6 even? 5.999. Here, I did it on Wolfram, and I got 5.99973. Okay, 5.99973. Well, cool. So that's those 2 points. Now, can we be more accurate? What do we assume the actual instantaneous rate of change is going to be? Probably 6, right? Well, let's see if I can add 1, 2, 3, 4 more zeros here, and 1, 2, 3, 4 more 9s here. 1, 2, 3, 4. 1, 2, 3, 4. Wolfram loves dealing with numbers. Well, look at that. 5.9999, lots of 9s here, 7, 3. Okay? Getting even closer to a certain value. I can go even further. 1, 2, 3, 4. Oops. I think I did 6. We'll go 6. 1, 2, 3, 4, 5, 6. It really doesn't matter, actually. I could. Pretty much they say decimal approximation 6. They said, I give up. All right, you got me. All right. That's the idea. What is this idea? It's using limits. It's saying we're getting closer and closer to 2 points being on top of each other, giving me a y value that's getting closer and closer to a certain value. How close? Well, it's so close, it's essentially going to be a number. And in this case, the number 6. Fantastic. We just took a derivative of a function. We found the instantaneous rate of change of this function at x equals 1. The function is increasing at a rate of 6 units per unit, 6 y units per x unit, right at the x value of 1. And we found f prime of 1, that is 6. Great. Well, we don't have our calculators in this class that often. And if we did this for every single problem, every single function, and every single x coordinate that we are looking at, that would take a long time, right? It's a messy calculation, involved plugging in a lot of stuff. It wasn't fun. So we need something else. We need like a formula. I need like a formula to find the slope of a tangent for any function at any location. Okay? So let's just take this f of x function. I'm going to say it looks like this, but it could look like anything else. And I'm going to say, let's find the slope of the tangent here at this location, x. Okay? Which could be any x value anywhere. Okay, we're going general here. We're taking a specific solution. We did like 3x squared. Instead, I'm going straight to x. Well, what's really interesting is that I don't necessarily need a point to the left of x and a point to the right of x to find the slope of the tangent. I actually just need the point at x and the point infinitely close to the point to the right of x. I don't have to go to the left and the right. It's actually going to be the same thing if I go right at x and to the right of x. So I didn't actually have to use one to the left and one to the right on the previous situation. I could have actually used one and one to the right or one to the left. As I got closer and closer and closer, I would still be approaching the slope of 6. Does that kind of make sense? Your 2 points that are infinitely close to the right and left, it's really going to be the same as just at the location and then a little bit to the right. Or at the location and a little bit to the left, okay? So that's important. All right. So I'm going to start with the slope of a secant line, and we're going to develop the slope of a tangent line. So I got 2 points here that make a secant line. And let's talk about the slope of the secant line. Well, slope is f of b minus f of a over b minus a. Well, I'm going to say this is a, and this is f of a. And then this point over here is going to be my b, and this y coordinate is f of b. Well, if this is some random x location on my function, this is going to be the f of x, or the y coordinate for x. Okay, so I got x and f of x. What I'm going to do for my other point, and this is going to be important, is I'm going to just make it in relation to x. I'm not going to say this is like x1 and this is x2. I'm going to say take this x and add a distance, h. So if I have x and I add the distance h, right here at b, this will be the x coordinate x plus h. And that means this function value up here would be f of x plus h. All right, so now we're going very generalized f of x's, and then we just have an h. Well, I'm going to replace the f of b, f of a, and b and a with my x and x plus h, f of x plus h, f of x. So let's see what that looks like. And you guys can do this. You don't even have to look up here and copy stuff down. Wherever you see f of b, replace it with this. F of a, replace it with this. Boom, there, boom, there. And we'll just all look up at the same time. That makes sense, Mr. Oshana. Good. All right. Mr. Oshana, can I do anything with that you can see? F of x plus h minus f of x, and now I have x plus h minus x. Yeah, I can simplify the bottom. Good. Well, let's simplify the bottom. I have f of x plus h minus f of x over just h. Okay, well, all of these three are just slopes of secants. And it's a slope of secant of 2 points with an h distance. Away from each other. Well, what do I need to do to turn this secant line into a tangent line? At x. What do I need to do to turn this secant line into a tangent line at x? Let's see what the tangent line, I'm not going to show you. If I put this point here, is my approximation going to be closer or further away for what my tangent line is going to look like? Closer, right? So what do I need to do to turn that secant line right here into a tangent line? Take this point and put it infinitely close to the other point, right? That's what we're doing. Take 2 points infinitely close together. If I took those 2 points and I put them infinitely close together, what's this red line going to do? Well, it's going to start here. It's going to track that other point, and yeah, you're going to think of it being smaller, but just think about the 2 points being kind of extended, and all of a sudden, boom. You just take those 2 points, you make a line, and you extend it. All of a sudden, this is a tangent line. Was a secant line with the point up here. Now it's a tangent line. What did I have to do to take those 2 points and move them infinitely close together? I had to make h smaller. How small am I making h? As close as we can get. Pretty much 0, but it can't be 0, right? What happens if h was 0? Then it's the same point, then we don't have a line anymore, right? It's the same point, it's undefined. Instead, we will take h and we will have it approach 0. Get infinitely close to 0. That's taking a limit. And what was a secant line formula becomes a tangent line formula. Here is a mystical, magical formula for a tangent line. It's a tangent slope. It's not a tangent line. It's a tangent slope because it's still from the slope formula. And when h approaches 0, now the 2 points are infinitely close together. Close together. Okay. This is our tangent slope formula. This can be used for any function at any location. Fascinating. If I just can find a limit of any function at any point, or as h approaches 0, but I'm using h as a distance, and I can use the point for any x, boom, I can find the tangent slope. And this is actually what we consider the mathematical definition of a derivative. Okay, we said it's a fancy math word for instantaneous rate of change, but we will say the definition mathematically is the limit as h approaches 0 of 2 points that are getting infinitely close together. It probably still seems weird to you. We'll apply it so you can see that it'll work. Now, the very important thing to know is that this came from the slope formula. You're going to forget this in the future. I'll remind you, this is just a fancy formula for slope that we changed. Okay? It came from just plugging different things in and simplifying and taking 2 points and putting them infinitely close together. It's just a slope formula that you are used to using. It just now looks different because we have h, which is a distance. And we're saying, all right, the 2 points that we're finding the slope for are infinitely close together. But it's still just slope. So that should be comforting to you, that this is just slope. These are 2 words you probably should know. Should write them down before we apply this fancy slope formula. Differentiation, that's like the process of finding a derivative. Finding a derivative, finding the instantaneous rate of change, finding the slope of the tangent. And differentiable means a function is differentiable if that x, its derivative, exists. We'll talk about that more a little bit later. Being differentiable, having tangent slopes that exist. All right. Let's do an example. Let's use this magical formula that Mr. Messner keeps talking about. Okay. If f of x is equal to 3x squared, we want to do, and I'm not going to say find f prime of x. I'm just going to say let's find, without using a calculator, let's find f prime of 1, which we already found using our calculator. We said it was equal to 6, right? Okay, let's do it without a calculator. Let's see if we can use the magical formula. Here we go. Well, I know that a derivative of a function is going to be using this. Well, there's actually nothing that we can't do. We can actually plug in stuff into everything except for h. Like, I know what f of x is. It's just 3x squared. So that means wherever I see f of x, I can replace it with 3x squared. And I can write down what f of x plus h is, right? So if I want to find what f of x plus h is, wherever I see x in my original function, I'll replace x with x plus h, typically in parentheses. Okay, well, now let's go ahead and substitute. And you're going to be doing this for your homework often, like 8 times. So be ready for it. Let's go ahead and substitute. We got 3x plus h squared minus 3x squared over h. Now we want to find this limit, right? But you guys know how to find limits. First attempt is to plug 0 in for h. If I plug 0 in for h, I get 0 over 0 undefined, right? Well, what's the second thing I should probably do? What do we think? This looks like a problem I've actually done before. You've all done before in Unit 1. Yes, let's distribute stuff. Why don't we try to algebraically simplify this to find this limit? Well, got to square the x plus h. That's x squared plus 2xh plus h squared. Divide it all by h. I have to distribute. What do I notice? The 3x squareds will cancel each other. Out of the remaining terms, they both share an h. I could factor out an h. The h that I factored out can cancel with the h in the denominator, now that we have multiplication in the numerator and denominator. And the final thing to do to find the limits is in my simplified function, I plug in the value for h. So I'm going to plug in 0 for h. And what do I get? 6x. What is that? What did I just find? I just found the derivative. Actually, it's even more fascinating than just saying it's the derivative. What we just found is a function, a friend to my original function. We just found f prime of x. What does that mean? That means that function can tell you the slope of the tangents to my original function at any point. This is like the good old buddy to 3x squared. 6x and 3x squared, best friends. 3x squared asks, hey, I don't know what my tangent is at 3. And then 6x is like, don't worry, I got it. It's 18. Okay? Good friends, best friends. This helps us discover the slopes of the tangents of that. I'm going to write it down. Friends of f. It will tell us the slopes of the tangents of f. So 3x squared is worried. He's not sure how he changes exactly at 1. Well, f prime comes in. He says, I got it, I got it, I got it. Just plug in 1 into me, and I will tell you the slope of your tangent. It's 6. Done. We don't need a calculator. You want to find the slope of the tangent of 3x squared when x is 1? You just say, well, f prime of x, f of x's buddy is 6x. F prime of 1, just like plugging in a value into f, you just replace 1 with x, you get 6. Hey, f is worried. He's not sure what his derivative is when x is 3. Don't worry. I'll take care of it. F prime of 3 is 18. Any value that you want. Turns out what we will discover is that functions will have their own functions, their buddies. Their buddies will tell us the slopes of the tangents of the original function. So we don't have to do it all at one location, 2 locations, 3 locations, multiple times. We can just find the friend, the buddy, and use him. Okay? Now here's the key thing to remember before we do the next question. That if you plug in x's into f of x's, you get y's. You combine them, you get a point on the function. However, f prime, the buddy to f, And each function will have its own unique buddy, okay? 3x squared is not going to work with 6x. I mean, 6x is not going to work with every other function. It's just with 3x squared, okay? But this buddy you're going to plug in x's to, and he's going to tell you and help you out with f. He will tell you tangent slopes of f. So if you are asked, what is the equation of the line tangent to 3x squared at x equals 1, you're like, all right, equations and lines. We just did that. We had a whole homework and a quiz about that. I'm going to need a point and a slope. The tangent line will be located at the point when x is 1 on my original function. So I plug in 1 into my original function, I get 3. The slope will be given by the friend, f prime, when 1 is plugged in. And I guess I should probably do that, this one. And I can combine that stuff, and I have my equation of my tangent line. One. Sorry about that. And if I had my calculator, or my friend, Wolfram, that's my friend, you can graph y equals 6x minus 1 plus 3. And y equals 3x squared. And we should be able to see the function 3x squared and its tangent line right at that location. Okay, so we did it. Now what I want you guys to do is kind of do the same thing, only develop the equation of the tangent line to the function when x is -3. And then I want you guys to confirm using your calculator that the line that you just developed is going to be tangent to your function right at x equals -3. You won't have to check with a neighbor, because if you have your calculator, you can check with your calculator by graphing 3x squared and your line. You'll have to solve for y, but you can simply just add this number to the other side. And you should be able to see 3x squared and your line being tangent to it. 27, negative 18. There's my equation. So I will graph y equals negative 18 times x plus 3 plus 27. And if all is right in the world, we have 3x squared. We have its tangent line right at negative 3. Fantastic. Okay. Now we're going to have to do this with other functions though. Same process, like maybe square root of x plus 1. Maybe we're going to have to find 2 over x plus 3. Okay? All these different functions, we're going to have to find its buddy. That's going to tell us the slopes of its tangents. How are we going to find the buddy? We're going to use our magical slope formula for 2 points infinitely close together for any function at any point. Okay? The definition of a derivative. Before we get to that, and I will show you this probably all the steps online, you're going to have 4 different types of problems. One where you're going to have to distribute to simplify just like we did there. We're going to have to multiply by the conjugate, an algebraic simplification step you remember from Unit 1. We'll have to find a common denominator, another step that you knew how to simplify from Unit 1. Okay, all this stuff we'll have to do. But before we do that, we need to talk about sketching tangent slope function. So we did find that what we started out with, we could find a function who can tell us the tangent slopes at any location. Well, we could also figure out the existence of these buddies graphically. Okay, so let's kind of do that. Here is a function. I'm going to move this x-axis up just so I don't confuse you. Say right there, and move this y-axis over. And I'll move this over to be right there. Okay, and here's the function. Go ahead and sketch this function. You'll need to see this. Okay. Now we talked about and we figured out that 3x squared has the buddy 6x that told us the slope of the tangent. Well, let's see if we can see graphically, if I have a function like this, what its buddy function will look like. Let's try to figure out what f prime of x would look like and what type of function it would be if this was f of x. Well, what can I do? Stay with me, Miss Grafford. Stay with me. I'm going to go ahead and write and sketch tangent lines, just really small tangent lines right on top of these defined points that I put down at -2, -1, 0, 1, and 2. Well, I know f prime values, my derivative values, my slope of my tangent values, are just the slopes of my tangents of f. So if I want to kind of say f prime at -2, what value am I going to use? I'm going to look at -2 for f, and I'm going to look at the slope of this line. And just for the purpose of this, I say this slope is just negative. We know that it's going down from left to right. So when x is -2, I'm going to go ahead and just place a negative value. Now what about -1? What is the slope of the tangent here at -1? 0, right? Well, at f prime, 0. When x is 0, here's my tangent slope. It looks like it's positive, so I'm going to go ahead and place a positive value at 0. At 1, I have another 0 slope. At 2, I have a negative slope. So we got slope that's 0, slope that's positive, slope that's 0, slope that's negative. Now here's a question. Do you think it's going to be safe to connect these points and kind of make this look like a smooth function-like looking curve? I don't know. Let's find out. Let's go to 0.5. 0.5. If I put a point right there and drew a tangent slope, it's a positive slope, right? Is it more or less positive than at 0? Less positive, right? So between 0 and 1, a less positive value right there. Between 1 and 2, between 1 and 2, we have another negative tangent slope. Is it more or less negative than this one at 2? It's also less negative. So what we'll find is that, yeah, we're going to be able to connect. And here is the buddy of this function. This is some sort of cubic function. I don't know exactly what the coefficients would be, but what is this? A parabola, it's some sort of x squared function. We just kind of found a situation that most likely these cubic functions, they're buddies that are going to tell them the tangent slopes, they're going to be x squared functions. Okay? We just figured that out. Let's take an x squared function. What's their buddy going to look like? A line. How do we know that? Well, we know that 3x squared, its buddy was 6x. Let's just kind of confirm it here. Positive, less positive, 0, negative, more negative. So positive, less positive, 0, negative, more negative. All of a sudden we have a line. And we start to see these connections. Now, before you leave, one more thing. It's very quick. Are there situations when we cannot differentiate? And that's yes. Derivatives don't exist when functions are not continuous. If you have a discontinuity, there is no tangent slope. The two other locations where you do not have tangent slopes are at sharp points like this, which is called a cusp, or this, which is like from some absolute function value. We would say that you cannot differentiate when x is equal to c. However, the derivatives exist everywhere else. What you will find is as long as you have a smooth curve, and I'll say it more specifically, the slopes from the left have to equal the slopes from the right, then we will have derivatives. However, we do not have tangent slopes at sharp points because the slopes from the left are not equal to the slopes from the right. If you have like an asymptote or a hole, you can't have a tangent slope because your point doesn't exist, okay? Good luck on your homework. Watch the rest of the video, which will be about 10 more minutes of me doing examples if you need any help. I'll also make sure I define this. Okay, let's be a little bit more specific. So when we cannot differentiate, yes, we cannot differentiate at a cusp or at a sharp point or at a discontinuity. But that's because this must exist for a tangent slope to exist. And how do we know when this will exist? Well, it's a limit, right? So limits have to exist. What does a limit have to do to exist? Well, the limits from the left have to equal the limits from the right. Well, in this case, since this is just a fancy slope formula, the limit from the left-hand limit, would be the slopes from the left. And the limit from the right, that would be the slopes from the right. So you can see here at this cusp, the slopes from the left are all positive and getting more and more positive. Okay? Positive slopes, more and more positive. But the slopes from the right are negative, but they're getting larger and larger negative. So we are approaching two different values right at this cusp. Thus, we cannot differentiate at x equals c. Okay? Same here. And it's just at c. I can take a derivative here. I can take a derivative anywhere here. It's just at this cusp. And right here at this sharp point, we have positive, 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 and consistent slopes. These are all negative, 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 negative. Okay? So since they're all approaching different values right at the sharp point, we cannot differentiate at that sharp point. Okay? So that's good to know. One more, maybe quick graphical. If I had something that was linear, what is its buddy going to look like? Well, this linear line all has tangent slopes that are all going to have the same slope, right? And what is the slope? It's going to be the slope of this function. So this is like negative, and this is negative. It could be like negative, 1 each time. So that means here, all of my tangent slopes are all going to be negative. So what was a straight line? Its buddy is going to be a horizontal line. Okay, which is pretty cool. I can give you a function. You might have to find what its derivative is going to look like. Let's see if you can figure that out. I'm going to look here. I'm going to see, okay, this is positive tangent slopes. And this is sometimes what I do instead of drawing. I'll just go straight to what the slope value is, positive. And then right here it's 0. And then these are negative tangent slope values, 0, positive tangent slope values. So we're talking about positive f prime values to a 0 to negative f prime values to a 0 to positive. B is the correct answer. Okay, that's good. Now let's finish off by doing 2 more examples of finding our magical f prime friend of f function that will tell us the tangent slopes of f at any point. So we already found it for 3x squared. Let's find it for the square root of x plus 1. All right, so we want to find the equation to the tangent line of this function when x is 3. Well, first I need to find its buddy. What is f prime? Well, it's going to be the buddy that's going to tell me the tangent slopes to the square root of x plus 1. Let's start by writing down our magical formula that will help us discover the buddy. Okay, we start out with that. Well, we know what f of x is. What is f of x plus h? Wherever I have x, I need to replace it with x plus h. So this is x plus h plus 1. Now what's really important is if they had another term, like if this was root x plus 1 plus 3x, you would need root x plus h plus 1 plus 3, and then in parentheses, x plus h. And it's important to make sure you include the x plus h plugged into x anywhere, just not at one location. Okay? So now, I will go ahead and substitute this in for f of x and f of x plus h. And now we need to algebraically simplify this to find the limits, because I can't plug in 0, I'd get 0 over 0. So this is when we remember, if you see square roots and limits, multiply by the conjugate. That'd be root x plus h plus 1 plus root x plus 1. Okay, and now let's see what we get. So this squared would be x plus h plus 1. This would be minus. Now it's very important when we're subtracting all of f of x, you'd put this in parentheses. It's very important to subtract the entire thing. Okay, so when I subtract that entire thing, I get minus the quantity of x plus 1. Don't forget that. I hope you're watching the video so you pick up that little key. On the bottom, we'll have the h times this quantity. Now we're ready to start simplifying. I will distribute the negative sign into there, the one that has h approaches 0. I find out that the x's will cancel with each other as well as the 1's. And what you'll find is if you're doing things correctly, you will see lots of things to cancel, and then you will be able to get rid of this h. In this situation, I do have h over h times that quantity. The h's will cancel. I will be able to find the limit as h approaches 0 of 1 over root x plus h plus 1 plus root x plus 1. How do I do it? I take 0. The last step is to plug in 0 for any h's that are left over. So I get 1 over root x plus 1 plus root x plus 1. That means that the buddy of root x plus 1, that's going to tell me the tangent slopes of f at any location is 1 over, and I'll just add these two together. I have 2 of them. Now that I have a buddy, I know the slopes of the tangents for f at any location. It's fantastic. So if I want an equation of a line tangent to this at 3, well, let's get my point. My point will come from my function. F of 3 is going to be the square root of 4, which is 2. So I get the 0.32. And I'll need my slope for my equation of my line. That'll come from my helper, my derivative. And I plug in 3, which will be 1/4. Then my line would be y minus y1 equals m, slope of the tangent, x minus x1. And that's it. We just did it. We found the equation of the line tangent to my function when x is 3. Let's look at the next one. Same type of question. The equation of the tangent line to the function at 2 over x plus 3 when x is 1. All right, well, let's start by using my formula. And let's figure out what f of x plus h is going to look like. Whenever I see x, I have x plus h. Now be careful again, if there's another x, make sure you add the x plus h into that x as well. In this case, we do not, so we don't have to worry about it. Okay, also remember when you are distributing, substituting in, make sure we subtract the entire right side. So subtract all of f of x, not just one term. Okay, very common mistake made. In this case, it's not that necessary because it's just 2 fractions. Okay, I need a common denominator in my numerator. You see, I have a fraction inside a fraction. We should be thinking fractions inside of fractions, common denominator. Well, it's going to be tough. You might think that all I have to do is just add an h here, but that is against the rules. If I add an h, that is changing what I have. I can't change what I have when I'm simplifying. I can just only make it look different. So what can you add? Well, you could add 0, but I'm not going to, that doesn't help me. So I have to multiply by something. So it turns out to find this common denominator, I have to multiply by this denominator. And then this, I'm going to have to multiply by this denominator. So I'm going to have to actually go a little bit more crazy than you would have liked to do. But it's what you have to do to get your common denominator. Multiply top by x plus 3 on the left. You'll multiply here x plus h plus 3. And let's see what I get. I'll go ahead and distribute the 2 times this quantity. This will be 2x plus 6. Then I'm going to subtract, and this is important. This is when we subtract the entire thing. Well, I'm going to subtract the entire numerator, 2x plus 2h plus 6. And then that will be divided by my common denominator, which is the quantity x plus 3 times the quantity x plus h plus 3. And then we remember that you can multiply by 1 over h, which is the same as dividing by h. Good. Let's distribute our negative symbol. That goes over here, here, and here. And we can see that the 2 x's will cancel, and the 6's will cancel, which means I'll probably be able to cancel this h with this h. Let's see what I got. The limit as h approaches 0 of negative 2h over x plus 3 times x plus h plus 3
Davy Rice is still
times 1 over h. The h's
please come to the front of the building
cancel.
at this time, please. Again, Davy Rice, if you are still in the building, you need to come to the front of the building. Thank you.
Okay, so the h's cancel. Then the last step is to plug in 0 for h. Don't forget this last step. Giving me negative 2 over x plus 3 times x plus 3. That is going to be negative 2 over x plus 3 squared. What did I just find? My buddy function that will tell me the tangent slopes of my original function. And this is what I'm going to use to find my equation of the tangent line. I will have my points, which will come from f of x. F of 1 would be equal to 2/4 or 1/2. And then my slope will come from my buddy function that will tell me the tangent slopes anywhere. At 1, we'll have 4 squared, which is 16, so negative 1/8. And we'll have the equation y minus y1 is equal to my tangent slope, x minus 1. Okay, that's it. Those are 3 good examples you need to follow for your homework. And then everything else, the drawing of our tangent slope functions, we see we can do. We see there are functions that are friends to original functions that help us find tangents everywhere. Very fascinating. Can't differentiate at sharp points, at cusps, or at discontinuities. That's it. Thank you.